Hi. Welcome to the first part of Chapter 3's lecture on stacks. If you looked at or watched the Week 3 at a glance, you saw that we're going to be spending 2 weeks on stacks. So this is part 1, and next week I will give you part 2. So let's go through this. Now, the objective of this whole Chapter 3 is, one, to explain the use and operation. How do you design it? How do you use and operate using a stack? Now we're going to implement a stack using a linked list, only because you can do it with an array, but it becomes more complicated than need to be. So linked list lends itself a whole lot easier than just an array. So we'll help you understand what the stack ADT is and how to write applications using a stack ADT, and then talk about some basic functions that are used, reversing data, parsing, postponing, backtracking, things that you'll be able to do with using a stack. Now, we're very used to stacks, stack of books, stack of coins, stacks in computers. Granted, you may not have been exposed to the third one, but that's the one we're going to talk about. But you think about, if I'm thinking about a stack of books or coins, when you put a new coin on top of the stack, where's it go? At the top. Stack of books, where's it go? At the top. How do I get to the last book in the stack? I've got to take all the other books off before I can get to that bottom one. So I've got to pop them off to get to the one I'm looking for. So conceptually, I think we can understand that. Now, some of the basic constructs that we're going to look at, for basic operations, we're going to go through about 8 different functions that are used. But just to help you understand this, it's pretty much, push is putting an item on a stack. Pop is a term that we're going to use to remove an item from the stack. And then stack top, it sends a copy of the top item in the stack, but leaves the stack intact. So it doesn't remove that top item. Where the pop, it copies that top item, but it also removes that top item from the stack. So it's taking that item off the stack totally. So just an idea here, you got a stack that starts off with 2 items in. I want to hit the operation push. I bring the data in, and the resulting stack is the original 2 plus the new one. And what does a pop do? Well, I started with 3. The pop, I get a copy of the data, and I remove it from the stack. But I also have to change the location of where top is now, right? Because you had 3 items there, now only 2 items, so the top of the stack has changed. So we got to keep in mind that location change. And then stack top is started with 3 items. I got the data, and the stack stays intact, so I still got the 3 items. So basically, like I said, stack top just gives me a copy of the data and leaves the stack intact. And here's just a brief section. I'm not going to go through it all, but it's basically, I'm pushing and popping different colors, so you can kind of see what goes added to the stack, what gets removed from the stack. I'll let you go through that in detail if you so choose. Now, since we said that a linked list is a very nice way of managing this, we're going to go through several things. One, we'll look at the structure. What data structure are going to be used, and there's basically 2. There's a data structure for the head, which is pretty much pointing to the top of the stack, and potentially data that could be stored. And then we got another structure of the data itself, what's getting stored in each of the elements of the stack. So you got 2 different data structures that are going to be used. 1 head, 1 data. And then there's a whole set of algorithms that'll be used. We'll go through, I think, 8 of them as far as this chapter is concerned. Now, let's talk about the head, the stack head implementation. Basically, generally, it only requires two data elements. One is the pointer to the top of the stack and the count of the number of elements. So that way it's very quick to know how many elements are in there and where the stack is located. Now, granted, it can include a whole lot of other information, average allocated time the item's been on the stack, how many times has it been referenced, who knows. But generally, most cases that we see, it'll have, tell me where the top is and how many counts, how many elements are in the stack. Now, that data node looks exactly like any other linked list item, which basically has what? Data and a pointer to the next node. Now, in this case, we're going to call it a self-referential data structure, only from the standpoint that each instance of the structure points to another instance of the same structure. So, not to get you bogged down in technical terms, but if you see that term self-referential, you kind of have an idea what we're talking about. Excuse me. Now here let's look at conceptually, what does it look like? Here's my physical stack. I got one at the top, but I got 5 elements in there. Well, physically on a computer, your head count says, yeah, I've got a count value and a pointer to the top. And then each node has a pointer to the next element in it up until I get to the very bottom one, which I've got a null pointer because it's not going anywhere. So these data nodes link to each other, and the head node keeps the count and pointing to the top node in the stack. Now, how's it implemented a little bit? Here you got structure of the two different lays. So you got a count and a top. So I've got a stack, count, top, and you could have these integers, floats, whatever the case may be. But top is going to be a pointer to the top of that stack. And then each node is going to have data and a link. And now this data could be a structure of data. It doesn't have to be just a single element. So it could be a node that consists of other structures in it. So your call. And just to give you a rough idea how that looks like. Again, the same red, green, blue stuff. But now I'm going to call the different types of routines. I'm going to call a create stack routine, which what? Before I had nothing, no stack existed. Now I'm going to create it. I've got to have an empty stack. So I'm going to allocate memory. I'm going to zero out the counter, and I've got no pointer. So I got it. And then the first push, I'm going to say I got it started out. Now I'm going to add, in this case, I'm pushing green in. So I'm going to still got the top is green. Still the end. There's only one element in it. So I've got to have that null pointer. And I've increased my count. So I've got to move the pointer to that first element and go on. Now, if I add that second element, I start with, here's my stack. Here's my head node. Here's my data link, the structure for the stack. Now I've added blue. I've moved the pointer from green, the top pointer from the green to the blue, and moved the link to the next item. So you see, so you can kind of get that same ish. And then if I'm popping them off, what am I doing? I'm starting with 2 elements. I'm going to take only off the blue. So I go to the top, pop, free up whatever space, decrement the counter, move down, and then if I do one more, if I destroy it, I end up freeing up all the allocated memory and such. And we'll go through some of that in detail. Now, like I said, there are probably 8 operations that are used in stack algorithms. 4 of them, the ones that I have in bold here, create, stack, push, pop, and destroy, are probably the most common. Stack top, stack empty, stack full, stack count are routines that, since we're doing an abstract data structure, those functions may be very beneficial to an application outside the ADT to know information about the stack itself. So create stack creates and initializes the head. Push inserts an element into the stack. Pop removes an element. Stack top, like I said earlier, it retrieves the data without changing the contents of the stack. Empty stack and full stack basically says return true if it's empty, return true if it's false in full. The hard one with that full stack is it's very difficult in some programming languages to implement, but we will give you an algorithm or two to try to conceptually understand what needs to take place. And then based on what language you're potentially going to use, may help. And then stack count just returns the number of elements in the stack. And basically what's that one? What do you think that's going to do? It's just going to return you the count value. And then destroy stack releases all the nodes back to main memory. So based on the programming language you're using and how it handles memory, allocation and deallocation is something that you may want to keep in mind. So let's look at each one of those in particular as far as the algorithm is concerned. So now we're still doing the linked list portion of it. So what's a create stack do? It allocates the memory and initializes the metadata. The metadata is the counts and anything else that in that head statement that you're going to do. So preconditions are none, and post condition is going to be a structure is going to be created, initialized, and I'm going to return the pointer to the head of that stack. So I've got to allocate the memory. My count is 0. My top pointer is null because I don't have any put any any data into the stack yet. And then I'm going to return the address of that head. So relatively straightforward as far as an algorithm is concerned. Now, a push, like I said, it inserts an element into the stack. Now, there's a couple things that need to be taking place. One, I've got to allocate memory for the node. I've got to put the data in the node. Then I've got to set the link of the node. I've got to at least copy the top of the stack address to the address of the link, and then update the top pointer. So I've just got to modify the pointers so that the top is now pointing to this address, and then update, because I got in the head node, I got to change that to top. I got to update, and then my pointer is going to do what? I'm going to point it to the top. And you got to be careful not to update your top pointer too quickly. Otherwise, you're going to lose your whole structure. Now, there's some conditions you need to keep in mind. What do I do with an empty stack? What do I do with data that's in a stack? And what happens if all the memory is exhausted? So these are things the algorithm has got to take into consideration when you're implementing it. Now, here are the 3 different conditions here as far as the push is concerned. So I'm not going to go through this in detail. You can go through, but basically I started off with, here's my new data that's going to go in. My existing stack was blue and green. And now here I've got the new one here. I got my new pointer here. I got to make sure I move that to top. But you don't want to change this too quickly. You want to make sure that you copy this link here first before you move the top pointer from pointing to blue to pointing to red. So you want to make sure this link is set before that. So the sequence of those links, because otherwise you break it too soon, you will lose access to your structure. So let's take a look at that algorithm. It looks fairly straightforward. So I'm going to put one item onto the stack. So my preconditions, I've got to have a stack that's passed by reference, and I have to have data that we're going to put on the stack. And of course, the post conditions are I'm going to receive the pointer back to stack with the new item put in. So I've got to allocate the new node. I've got to store data into that new node. Then I got to make the current top pointing to that second, to the second node. And then make the new node the top. It's this sequence here you got to make sure that are the right order. And then increment the count. So fairly straightforward, not overly complicated. You'll see the code, at least in C, a little bit later. Now, let's look at what I have to do to pop. I think I do that. Yeah, push, this is pop. Okay. Now, basically what do we get? I get a copy of the data that's on the top of the stack to the calling algorithm. So first thing I'm doing is I send the data, and then I adjust the pointers to logically delete the node. So I'm just going to, basically, what am I going to do? I'm going to move the top pointer, and then I'm going to delete the pointer pointing to that second item, delete that. Then I can physically delete the node, free up that memory, and then adjust the count. And then, of course, return, was it successful or unsuccessful as far as, popping that item off the stack. So here's a rough schedule. So again, you get the stack that was passed by reference, and you get the data that is reference variable to receive the data. So I got to store that data someplace. So in this case, data out is going to be the variable I'm going to put that data into, and then returns true or false. And then out is return the value of the calling, plus I'll also reduce the size of my stack. True if it's successful, false if I've tried to allocate or pop off something of an empty stack. So here it's like, is the stack empty? If it is, I'm returning false, because that means I've now hit that underflow piece. If it's not empty, I'm going to set data out as to the data in the top node. I'm going to make the second node now the top node, decrement the stack count, set it to true, and then return success. So just thought I'd let you know that is the case for how to do a pop. We'll go through some of it. So here's just a brief pictorial thing is what? I've got my 3 counts here. I want to pop off that top item. So it started here. I'm going to delete this pointer here. So I got to move my top, break my link here. I'm first going to take this, move this, get rid of the link, move my top pointer down, and then recycle all the memory that was there. Now, stack top, like I said, all it does is it doesn't delete the top node. It sends the data of that top node to the stack. So here, if it's, all I'm doing is retrieving the data from the top. So if it's empty, return false. If it's not empty, I'm just assigning the data in top node to what I'm going to pass back and set the success to true and then return success. So it's a fairly straightforward the stack is still intact and everything's just fine. Empty stack. Basically, what am I doing? I am just, now granted, if I'm working with data, I put those in, this one in place along with a couple others, the next 3 or 4, only if I'm doing this as an ADT, abstract data structure, because I'm hiding the data. So that way the end application user can have other checks. So I usually wouldn't implement this if my algorithms had total access to all the memory and all the data here. But all it does is determine if the stack is empty, and really all it's doing is checking the count. Is the count 0? So is the stack count 0? Return true, otherwise false. It's fairly straightforward routine. Now full stack, again, only implemented if I'm hiding the data, but based on the language, very hard to code. I'll give you an algorithm, but then it's going to be based on your the software you're using, the compiler you're using to see if it's even doable to verify. So my precondition is I've got a structure with a valid address, true if it's false, true if it's full, false if there's still memory available on your machine. So if memory not available, I'm going to return true. If it's false, otherwise return false. So it's not that complicated, but the hard part is can I tell if there's any memory available? Now, stack count, what am I returning? I'm just returning the stack count in that head node. All I'm doing is returning that value. I'm not processing links. I'm just going to the head node, read the count, return it. Now, destroy stack deletes all the data in the stack, frees it all up, deallocates all the memory so that everything is cleaned up. So basically all I'm going to do is got to get a stack by reference, and when I'm done, empty, and all nodes are deleted. So all I'm going to do is loop through the stack, delete the top node, and I'm going to keep looping through, delete the top nodes, and then once it's all done with the loop, I'm going to then delete the stack head. So all I'm going to do is a series of pops to get rid of, that top node and go from there. Now, let's look at, we talked about stacks, and let's talk about implementing a stack ADT with its structure and maybe its applications, but we'll actually develop some of the software with it. So look at the data structure, and we'll look at implementation of those different structures. Now, with C or C++, this is relatively straightforward. You don't have to store data. You just have to have the pointer of the data. The application's responsible for allocating all the memory, and a stack node looks just like a linked list. And then the head node and data are all encapsulated inside the ADT. Now, what are the two structures? Well, you got a node which has what? The data pointer and the link pointer to the next node in it. And what's the head structure look like? I've got a pointer to the top of the structure and then a count of the number of elements. Rough idea what it, graphically, what you're going to be. So, because all this structure here is in the ADT, your main's only saying, hey, I just want a stack. So I'm hiding all this information away. In C, we're not going to make you C coders, but we're just going to quickly go through some of this stuff. But here's an example of what I got. I've got a pointer to the next piece of data, and I've got, now this is your structure. It's a node. This is your stack node. So inside of that node, and now I've got the head node here as far as, and they just call it stack. So I've got a pointer to the top and the count. So two different structures, how in C language you would declare it. Now, if I was going to create it, so what am I going to do? I'm going to call it, the routine is going to be called create stack. Now, if you've caught up on some of your reading, when you pass a void, now I can say all these, I don't have to worry about what data am I passing. I can write a generic routine that C will then allocate based on the different types of pointers, the different data types, whether it's a float, a character, integer, it'll handle that for us. So I got my local definitions, define a pointer to the stack. And here, what am I doing? Because I'm creating it now, I've got to allocate the size of the stack. So I'm pointing that first address to allocating that first bit of information. I changed the count to null, and the counter at the top is null because I don't have anything in the stack yet. So that first address is empty. So this link here would be null. And that would be the routine, the C routine for creating stack. Now, push. So I'm going to give me a pointer to the stack, and I'm going to say, give me a pointer to the data that's coming in. So that's the data that's going to be inserted here. So I'm going to have a new pointer to the new node I'm creating. I've got to allocate the space for that new node, call that new pointer, and then just making sure that the memory was available. I now move the data into the structure, into our node data, and then now change the pointers. Now I changed, because this is now the first one in, I changed the stack to the top of that address and the new pointer, and then move the new one to the top. And then increment in the head count, the count. Increment it by 1. And that's what this function here is doing. Pop. Basically, this is what I've got. I'm getting a pointer to a stack. And then this is where I'm going to store the data on the way out that I'm popped off of the routine. So what do I have? As long as I've got a count. If I got no count, I'm done. But if I'm, because all I'm doing, remember this is stack top, all I'm doing is just pass on the pointer, tell me what data, basically what's the address of that data that's stored in memory, and that's all I'm returning. Now empty, again, fairly straightforward. I got a pointer to the stack, and I'm just checking if the count is 0. If the count equals 0, I'm empty. If it's full, like I said, this one is a little bit more complicated. It may or may not work in the application doing, but this gives you a rough idea. So I'm passing back the pointer to the stack. I'm going to give myself a temporary node, and now I'm going to say, because what am I trying to do? I'm trying to check if it's full. So actually I'm going to try to allocate another node. If I do, it's free, go ahead. Otherwise, if the allocation failed, then go ahead and return. Stack count, all I'm doing is returning the count in the head node. Now destroy, a little bit different, because what am I doing? I'm going through, I've got a loop statement, and while that top is not null, I'm going to free up the pointer. I'm going to move my top to memory. I'm going to move my links, and then free up that temporary one, and just keep looping through until the top one is null, till that stack top is null. Then I can totally free the head node and then return. So hopefully this gives you a rough idea of some of the functions in an ADT as far as the stack is concerned. We'll look at applications of this next week, but hopefully this gives you a little bit of the theory behind, or at least the algorithms behind, some of the stack information. If you have any questions, feel free to ask.